Welcome to my Alum postlab video part 3. First, crystals. I finally have crystals. There's one large crystal against the side, and if you can see, there's a lot of small ones scattered along the bottom, and also a cloud of precipitate that is hasn't crystallized yet. It's just floating above it. So this week I had my crystals right next to the window, and last video I talked a little bit about how I thought sunlight might play a role, but now I'm pretty sure it's because of the coldness of winter outside that lowers the solubility of the solution and enhanced the rate of crystal formation. So I have one large crystal, but there could be many ways to expedite the process and have a method to make one large crystal in the middle. So I think hanging a string, if you put a lid on top of the bottle with a string hanging down into the middle of the solution, that would provide a seed or somewhere for the solution to latch onto for when it comes out and make a bigger crystal there, acting like a seed. Also, as I talked about, coldness in front of the window can make the process happen faster. So these are both, I think, potential methods to grow one large alum crystal. So now I'm going to talk a little bit about D-spacing and Bragg's equation. So in a solid, in a crystal, there's a lot of different planes where all the atoms are. So there'll be a bunch of atoms in each one of these planes, and D-spacing is the distance between each one of these planes. And if we know the space between them, then we can reconstruct the crystal and better know the locations of the different atoms. So what Bragg discovered is that X-rays are the perfect light to pass through the different planes and then bounce off in predictable ways. So in this diagram, each one of these lines are different X-rays, and they come back. Since each of these planes in the solid are parallel, then the angle in is the same as the angle out, and they arbitrarily will pass through some planes and bounce off of others, which is why this X-ray went through this plane and the other one bounced off of it. So this triangle right here is the difference between the two waves, which represents, here I represent put the triangle here, which represents the distance between the planes, which is the D-spacing. Using SOHCAHTOA and trigonometry, we can develop this equation. Sine theta equals 1/2 the path length divided by d, the distance between the path lengths. So we want to solve for the path length. So let's rearrange this equation. Equals the difference in path lengths. There we go. So what Bragg discovered is that if you want the phases of these two waves to match up when they come out, then it has to be then this section has to be equal to some number times the wavelength. So now we get this. This is Bragg's law here. So he related the wavelength to d, which is the distance between planes again. And this is, again, helpful to reconstruct a crystal and figure out where all the atoms are. So now we're going to transfer to, this is to figuring out for our particular alum crystal what the D-spacing between the different planes is. So this is a reproduction of the graph that was given from X-ray diffraction on our crystals. And 2 theta, the degree here is 20. So it's 2 theta versus the intensity, and we're going to calculate it for the highest point, which is this one right here, which has a 2 theta of 20 degrees. So 2 theta equals 20, which means theta equals 10. And then if we plug this, I'm just going to rearrange Bragg's law to solve for d. Sine theta. If we plug in our theta on the wavelength that was given here, on the graph. 4 divided by 2 sine of 10. Then we get a d equals 0.444 nanometers. So this is our d spacing between the planes in our alum crystal. And again, now we can begin to map out the crystal and figure out where the atoms are and visualize the structure. So this concludes my third post lab video. I hope you enjoyed it, and have a nice day.